Hello guys, my name is Vuthyra Oup and I'm currently a sophomore at Paragon University. Welcome to my PermaLearn walkthrough video. Today I'll be demonstrating one of the most useful tools that engineering students use inside PermaLearn, or we can call it 2D structural analysis tool. I'll guide you step by step through how the tool works, what each part of the interface does, and how we can use it to solve a real engineering problem involving distribute load on a beam. The goal of this video is not only to solve the problem, but also to make sure that if this is your first time using PermaLearn, you will understand everything clearly and be able to repeat the process yourself. By the end of this video, you will know exactly how to use the tool for exam assignment or to practice. Before we jump into the structural analysis tool, let me explain briefly what PermaLearn is, especially for those who might be new. PermaLearn is a modern online learning platform designed to help students learn difficult engineering topics in a more visual and interactive way. Instead of only using PDF, textbook, or lecture, PermaLearn gives us interactive tools that let us simulate engineering problems. For example, in subjects like static mechanic of material, structural analysis, dynamic, and even strain of material, PermaLearn has built-in calculator and visualization tool that help you check your understanding. This tool is allow you to see what's happening instead of just memorizing formulas. One of the most powerful one, and the one we using today, is the 2D structural analysis tool. This tool uses the finite element method to analyze beam, find reaction force, draw shear force diagram, bending moment diagram, and calculate internal force. Now, let's jump into the tool. Here on PermaLearn homepage, I navigate to the tool sections. Inside the tool, you will see a list of different categories. Once you click it, you will see an interface that looks a bit like engineering software. When you first open the tool, you grid by three main sections: the input panel on the left, and the modeling grid in the middle, and the setting panel on the right. Let me explain each one clearly. Left panel, input sections. This is where all the engineering definition happen. You can add member, support, hinge, joint load, point load, linearly distributed load, temperature change, fabrication error, support settlement, and solutions. Each category has its own input field. Now let's go to the middle panel or the grid. This is the visual area where your structure is displayed. When you add member, load, or support, it shows up here. The right panel, analysis and options. Here you can set a unit, a grid line, number of finite element, or the mesh size. And you have a button to clear everything or the cell to save the model. The example or the exercise we will solve today is from engineering mechanics static from figure 7 5a. The beam is 3 meters long, fixed at point A on the left and free at point B on the right side. A triangular distribute load acts on the beam starting at 1200 Newton meter at A and decreasing linearly to 0 at B. Point C is located exactly at the middle point of the beam and 1.5 meter from A. Our task is to determine the normal force, shear force, and bending moment at C of the beam. We will model the beam in PermaLearn and extract the result directly. First, I go to the member. I set the begin x coordinate to 0 and y to 0. Since the beam starts at A, the horizontal distance is 3 meters and the vertical distance is 0 because the beam is horizontal. Then I click add. Now you can see 3-meter beam appear on the grid. Next we go to the support tab. At the joint coordinate, we have x equal to 0 and y equal to 0. And I selected the fixed support type. A fixed support is different from a pin. It restrains rotation and translation just like a wall. After we clicking add, we can see the yellow point here. The fixed wall symbol show up at the left end of the beam. And then next, we don't have a pinch, joint load or a point load on our example. So we go to the linearly distributed load. Our example, we have one member and then the load type. As you can see our example, the load type is vertical load. And our distance from the begin joint is 0. Distance from the end joint, if we don't have it, but we have it, the begin load is 1200 Newton meter, but it's downward, so it will be negative. Our system is kilonewton, so it will be negative 1.2. and load is 0. Now we click to add. The triangular load appear, decreasing from left to right. Now we go to solution tab and click calculate. PermaLearn process the beam using the finite element method and generate reaction force, shear diagram, bending moment, and internal force distribute. To find the internal force at C, we go to the normal force and then click display. You can see the red line here. But to get more point, we go to the mesh size and set it to 0.5. You can set it as small as you can. Go to save option. Now you can see the middle point here. The middle point here is x equal to 1.5 meter. The normal force is 0. The PermaLearn show the internal force value directly. So it's 0 because there is no horizontal load. Now we go to the shear force. Click this shear force and then display. The shear force is negative because the load is applied downward. The shear diagram decreases linearly because the triangular load decreases linearly. And the moment diagram is smooth, is a smooth curve, and the magnitude of the moment decreases toward the free end. Now we go to the bending moment. The bending moment is negative. PermaLearn help us visualize how the cantilever respond under loading and allow us to check the internal force at any location. So that complete our detailed walkthrough of showing a fixed and cantilever beam with a triangular load using a PermaLearn 2D structural analysis tool. We build the beam, add a fixed support, apply the triangular load, ran the analysis, and extract the internal force at point C. Thank you for watching, and I hope this help you use PermaLearn for future assignment and a project. That's all.